Actually, right.
All right, so if you are a saturated hydrocarbon, that means you're full of hydrogens. If you're unsaturated, that means somewhere there is a double bond or a triple bond. So we looked at double bonds, and what is the special ending that we use to describe the fact that we have a double bond somewhere? -ene. But can we have a triple bond somewhere? Yes. Triple bonded hydrocarbons are called alkynes. Alkynes. Let me differentiate between them so that you know what to look for. If it's an alkane, it should be CXH2X plus 2, like C2H6. That's an alkane. If you encounter something that is CXH2X, like C2H4, then there is a double bond somewhere. It's called an alkene. But if you encounter CXH2X minus 2, C2H2, then there is a triple bond, and it will be called alkyne. An alkyne. What are the rules? Very similar. So similar that this summer when I was doing this, I copied and pasted from double bonds. You might want to check your notes. I think I fixed the notes now. But this word right here should be triple, not double. Triple, not double in your notes. So count the number of carbons in the longest continuous chain. Number the C's in such a way that the triple bond is on the smallest numbered carbon. Write the number of carbons previous to the triple bond. So it's the triple bond will be following the carbon that you need to number. Follow the same rules as alkane, except that you add a Y and E instead of an A and E. The triple or double bond will be the most important thing. So once you've numbered that, then any branches will be stuck with whatever number they are. So if you number the double bond to be on number 2 carbon and you have branchings down the line, then those branchings will have a larger number than they should. Okay? You've played cards. You know that a king trumps a queen trumps a jack. Well, in chemistry, a double or triple bond trumps a branch. You'll see what I mean later. All right, here we go. Jeffrey, name this thing. Okay, that's a good start. Butine. You can be a Westerner and go left to right, 1, 2, 3, 4, and call it 3-butine, or you can be an Easterner and go right to left, 1, 2, 3, 4, and call it 2-butine. What's it going to be? I'm sorry. No, I'm sorry. It would be 1-butine. 1-butine. Okay, 1-butine. Yes? Yes. Because there's an isomer of this. Can somebody describe what another possibility could be? What's an isomer? Same formula, different structure. What's an isomer? Asher? Yes. What if we were to move the double bond over following number 2? Triple bond, I'm sorry. What would this be called? 2-butine. Is there another isomer? Can you have a 3-butine? Why not, Kelsey? Yeah, because that would be the same as a 1-butine. And you have to go in the direction that gives you the smallest number. Emily. What would you call this one? One step at a time, Emily. Longest continuous chain.
Oh, is that
Hex. Hexine. And if I see yne, I want to know where the yne is located.
3?
Yeah, good. Okay, Emily, give me an isomer for this one.
Yeah, 4?
Okay, at that point, if you move it over here, you can't call it 4-hexine. Why not? Because you're being very west. It would be what?
2 hexine?
Yes, thank you. You gave me another isomer. Good. Gracie, give me another isomer.
1.
Yes. Be careful. Got to make sure you have the right number of hydrogens. So 1-hexine. Emmy, give me another isomer. Get off the yne thing. No more ynes. We are now done with all the different isomers that could have the triple bond in a different location. You can't have it anywhere else. So, now it's time to cut and paste. Do you know what I mean by that? Okay, give me a possibility here. So, cut that off and paste it where? This one right here? Okay. I like it. Good job. Let's name it. Which pentyne? 1-pentyne. Once you number it in a certain direction, in order to give yourself the smallest number possible for the triple bond, now you're stuck. You can't number it in 2 different directions. Yes. Did you see what happened there, gang? Okay. Once we numbered it in this direction, in order to give the triple bond the smallest number possible, now we're stuck. But that gives us a big... Okay, too bad. Because what's more important, the double/triple bond or the methyl group? The double/triple bond is more important. Can you imagine how many more isomers we can come up with this? Because all we have to do is now change the triple bond over here, and that's a different isomer. Or we can change the methyl group over here. That's a different isomer. This could go on and on for a long time. Yes? I do not care. Devon, what's this one?
I have no clue.
What's the longest chain?
2. No.
Most people would say that's 3.
Oh, I didn't know.
1, 2, 3. Okay, so what is the prefix for 3?
Drop.
Nope. Look on the first page of your notes. Should be on there. Top. Help him, Gracie.
Oh,
Prop. Okay. If you have a triple bond, how do you end it? Now go back to the page that we're on. How do you end triple bonds? Help him out, Gracie. Yne. Good. Yne. All right? And where is the yne located? After the first carbon, after the second carbon, after the third carbon?
After the second.
Yes, if you are numbering from right from left to right, but what if you number from right to left?
After the first.
So you gotta always have the smallest number possible. Can somebody give me another isomer for this one? Another isomer. Keeping in mind that the answer could be no, there's no other isomer. Yes.
Could you lop one off to the side?
Very good. Can you lop off that right there and connect it to the one of these? Can you, folks? No, because that is just a bend. You can't have any branches on the end because it's not a branch, it's a bend. There aren't any more isomers. Rica. 3-heptine.
7 carbons.
And?
After the third one, there's 3.
Okay, this is the hard part, making sure you have the right number of H's. How many?
3, 2, 9, 9.
Good.
2.
Good.
2, 3.
Yes. Good job. Ethyne. Spencer. And where is the triple bond? How many H's? How many H's? Good job. Serenity, 3-octine. Oct.
8.
What does the ine mean? That would be ene.
Oh, that's right.
Single, double, or triple?
Single?
That would be ane. One left. Yes! Good job. Where is the triple bond located? Past the first, second, third, fourth, fifth, sixth, seventh, or eighth? Very good. Now comes the hard part. That was easy. Now comes the hard part, making sure you have the right number of H's. How many H's? 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 Very nice. Very nice. 2-pentyne, Randy. Any day now.
I see. I don't know where. I don't know. I can go after.
Okay, you go there. YNE stands for single, double, or triple bonds. That would be ENE. Try again. That would be ANE. Try again.
Triple.
Yes, good job. Where is the triple located? After the first one, after the second one, after the third one, fourth one, or fifth one?
Second or third. Second.
Good job. Now,
How am I supposed to know which one?
It says that depends on the 2, right?
Oh,
Okay, so that does depend on the 2. Okay. So,
how many H's? How many H's? Carbon has to bond 4 times.
3.
How many H's?
None.
How many H's?
None.
How many H's?
2.
How many H's?
3.
We've talked up carbon quite a bit here on Crash Course Chemistry, but we really haven't justified the lofty position I put it in. Just chains so far, and while chains are good, they're not enough reason on their own for this high level of esteem. But carbon atoms, they do more than just form chains. Sometimes they form rings, or as chemists call them, cyclic structures, and if the rings have the right number and placement of double bonds, they start acting weird and wonderful. The compounds made from them are called aromatic, literally because they have aromas. They can smell amazing. Basil, vanilla, cloves, tarragon, lemon, cinnamon. When we smell these things, it's because aromatic compounds, compounds with carbon rings, are binding to receptors in our noses that tell our brains, OMG, tasty stuff nearby. Of course, mothballs and modeling glue and lots of other stuff are also aromatic and don't smell so good. But if you've ever smelled an herb, taken medicine, worn clothes, or enjoyed a meal, you probably owe that experience, at least in part, to aromatic hydrocarbons.
Aromatics. If it has an odor, folks, it's an aromatic. So what's an aromatic? All right, let me give you the story. This is actually, according to the scientists, it's a true story. All right, by the mid-1800s, they had isolated one of these aromatics being C6H6. That was its formula. So they started trying to figure out what it looked like. Okay, 6 C's. Yay, 6 C's. 6 H's. Well, that looks kind of funky, yeah, 6 H's. All right, so that means there must be some double bond somewhere. Double bond. Okay, that satisfies this one, but then you need another H here, which you don't have. This carbon's okay, and this carbon is not okay, so you don't have another H here, so you put a double bond there. Okay, good. So that carbon's okay, and that carbon's okay, but this carbon is not. So you put another double bond there, and this carbon's okay, but this one is not. What are we going to do? Could we use triple bonds? Same problem. They were stuck. This guy by the name of Berzelius Gekule, German dude, maybe Austrian, I don't know. He went to sleep one night wondering about this, and he had a dream of a snake biting its own tail. A snake biting its own tail, and then he got up and went, I got it. So, no one had ever thought of this. But what if you had 6 carbons and they had turned into each other so that the head was biting the tail? 6 H's. Now alternating double bonds. That works. They had discovered ringed hydrocarbons, and ringed hydrocarbons were all over nature. Anytime you smell the fruity smell of lemon or oranges, you're smelling a ringed hydrocarbon. Any perfume is a ringed hydrocarbon. Actually, the more they study this, the more they realize that they were dealing with a chemical that was all over the place in Mother Nature. What are aromatic hydrocarbons? They're not always 6-sided, but typically for our purposes, they're 6-sided hydrocarbons with branchings stuck to it. Branchings stuck to it. The most common aromatic was benzene.
Example, this ring has 5 carbon atoms in a double bond, so it's a cyclopentene. It has 2 branches, an ethyl group and a methyl group. We list these in alphabetical order in the name, and we number the carbons in the ring so that we get the lowest possible numbers on the branches and on the double bond. If we number counterclockwise from the beginning of the double bond, we get the branches at the 2 and 5 positions, but if we number clockwise from the double bond, the branches are at the 1 and 3 positions. So this must be 1-ethyl 3-methyl cyclopent-1-ene. But since there's only one double bond and it's in the first position, the second one is often left out as being understood. So we simply call it 1-ethyl 3-methyl cyclopentene. Incidentally, all of the identifying parts of an organic molecule, the double and triple bonds, the carbon chains that branch off the main chain, those are called substituents because they substitute for hydrogen atoms. So far we've just been looking at the cyclic hydrocarbons. So what's up with the aromatics? How are they different? Well, this is one of those times when carbon starts doing some of its spectacular dances. Cyclic hydrocarbons that contain resonance structures. Things are getting interesting. And by interesting, I mean, what? Resonance occurs when electrons are distributed around the molecule in a way that makes it impossible to draw with a single Lewis structure. It's a limitation of our tools to represent the beauty and complexity of reality. In a resonance structure, the real-world structure of a molecule is essentially an average of all of the possible structures that we can draw. The simplest aromatic hydrocarbon, and one of the most common, is benzene, C6H6. It's the pungent compound that gives gasoline its strong, sweet smell. It contains 3 double bonds, so that each carbon has a total of 4 bonds. We normally write this and other organic structures without the hydrogens in order to simplify things, and we often don't even write the C's for the carbons. Every corner is assumed to be a carbon atom, and since we know that carbon needs 4 bonds, it's easy to figure out where the hydrogens belong even when they're not written. Here's the thing though, those double bonds could just as easily be in these positions, and they are in those positions. Sort of. Remember, their draw bonds are in both places, so the actual structure is essentially an average of the 2 drawable Lewis structures. That's resonance. It's reality poking us in the nose and saying, oh, you thought you were so clever with your Lewis structures, but in this situation, they are useless. To show that the double bonds aren't in any specific place, we often just show the structure with a circle in the middle, signifying that the double bonds are averaged in a ring throughout the benzene group. Aromatics can have all sorts of substituents as well, and the naming system is pretty much the same as with other cyclics. Another example. So this is a benzene with 2 methyl groups on it. As always, we number the rings so the branches have the smallest possible numbers. In this case, if one of the methyl groups is in the 1 position, the other is in position 2. Note that the numbering could also be done like this, but it doesn't matter as long as the branches are at the lowest possible numbers. That makes this molecule 1,2-dimethylbenzene. Now, if you swap the methyls out for a couple of other slightly more complicated groups, then you get acetylsalicylic acid, or aspirin. Aromatic rings can be used the other way around too, as substituents onto hydrocarbons. Circle this molecule, a hexane with a benzene ring attached to carbon number 2. When benzene is used as an attachment, we call it a phenyl or phenyl group, so this is 2-phenylhexane, or 2-phenylhexane. It doesn't matter. What's important is that it is not a benzyl group. Why? Well, it was English genius Michael Faraday who first isolated benzene in 1825 from the gas used in lamps, and in honor of this, his French contemporary chemist Auguste Laurent started calling the derivatives of benzene phen, from the Greek for I illuminate. It's a lovely gesture, very sweet, but like, seriously? But just to make sure you're like good and solidly confused, benzyl groups do exist. They're a phenyl group joined by a methyl group instead of just directly. So now that we know where the word phenyl comes from, I bet you're just salivating with curiosity, wanting to know where benzene comes from, because, like, your desire to know things is stronger than any of your other desires, right? Yeah, I thought so. So here's how it happened. Back in the 1400s, when the spice trade drove the majority of the global economy, Arabic traders sold European traders a resin used in perfumes and medicine that they called lubanjawi, or ensigns of Java. Of course, it didn't come from Java, it came from Sumatra, but the world was a big and complicated place, so we can't really blame them for being a little bit confused. The lu was mistaken by the Italians for the definite article la, and so it was dropped, making it banjawa, and then the French called it banjois, and eventually the German and English made it benzoate. This is also, by the way, the same root as the name Bon Jovi. It's not. When we started doing some chemistry, we found that most of benzoin was composed of an acid which chemists named benzoic acid, or acid of benzoin. Then, a little chemistry knocked the acid off, creating what was clearly an alkene, so they named it benzene, because it was an alkene that was from the benzoin resin. History is hiding everywhere! And so is chemistry. Now, benzoic acid is one of literally infinite possible benzene-based compounds. There's naphthalene, the main ingredient in mothballs. It's basically two benzene rings stuck together. And there's anthracene with 3 benzenes, which is probably the dye that's making your blue jeans blue. And it can get crazy complicated all the way up to humic acid, a component of soil. Now, you might be...
Guys, I mean, we're talking extremely important. Benzene is probably one of the most important chemicals in your life. Next time you go to CVS and get some medicine, open up the little pamphlet that you never open up. Somewhere there is going to be the structure for the medicine. You will find this structure or this structure. More than likely, there is benzene in your medicine. Here is the fun part. Take the benzene and add an OH to it, and now it's called toluene. If there is a nitrate on it, it's called nitro. If there is 3 nitrates on it, it's called trinitro, which is what? Dynamite. Trinitrotoluene is TNT, and it's all based on benzene. Get your work done. Get your homework done. It should be fairly easy.